So, thank you, Luis.
Can you hear? Yeah, I think it's loud and clear, right? Okay, well, so we go from gravitational waves back to neutrinos, and in this case to neutrino interactions. And well, as you know, neutrinos are everywhere, which means that neutrino interactions are going to be present, even if they are rare, everywhere where matter is, because neutrinos were already there, we know. So if there is matter, there are neutrino interactions. And these interactions are pretty much shaped, defined by the properties of these matter systems. So by the properties of hadrons and nuclei, and well, as we learned yesterday, even neutrinos themselves, if you have enough amount of them, they can make a medium with which other neutrinos would be interacting. So actually, I remember that a few years ago, it was suggested there was a paper that suggested that you could that the supernova explosion could be boosted if nucleons had um, a significant amount of SS bar, so strange quarks. Strange quarks are not present directly as a constituent quarks in the nucleons, but you could have SS bar pairs in the nucleon. So nucleons might have a strangeness content. And there was a suggestion that if the strangeness content of the nucleon spin was big enough, this could help boosting the supernova explosion. Probably the values that you need for that to happen were too high and in contradiction with the determinations of this strangeness content of a nucleon spin that was made in the lab. But I mentioned this because I think the example illustrates what I meant by properties of the medium, properties of hadrons and nuclei having a direct impact on how neutrinos interact in all the systems that we have. And of course, there is another, so the opposite is also valid. Neutrinos probe matters in a way that no other probes can do because of the fact that you can change flavors in charge current interactions, because you can you have this unique combination of vector and axial vector contributions in the interaction. And besides that, of course, obvious as it might be, neutrino interactions are doorway to neutrino properties. Maybe I should use the word portal, that is nowadays more fashionable. So we can only learn about neutrino properties because in our neutrinos interact once in a while with our detectors. So that's the way in which neutrinos were discovered in the first place, and that's what allows to determine neutrino flavor, which is of course something you definitely need to study oscillations. You rely on charge current interactions to detect a muon or an electron, and then based on that you can study oscillations. In addition, every oscillation experiment, in particular, I will be having in mind experiments with accelerator neutrinos mostly, but the statement is general. Oscillation experiments rely on good knowledge of neutrino interactions for a number of tasks they have to do. For flux calibration, very important aspect is background determination. You have to reduce the background, and neutrino energy reconstruction. So why neutrino energy reconstruction is an important issue? Because, well, you cannot, neutrinos are, well, weakly interacting, they are neutral. You cannot easily make a collimated beam of neutrinos. The way neutrinos are produced in accelerator experiments, you have usually, you accelerate protons that hit the target, and in these collisions you produce charged pions, which then decays into charged muons and the corresponding muon neutrinos and antineutrinos, and then later the muons themselves decay weakly, giving you a combination of neutrinos and antineutrinos of mostly muon flavor, but also there is some contribution from electron neutrinos. And of course, with the charged particles, you can then use magnetic fields to separate them and create beams in which you have a major contribution from neutrinos or a major contribution for antineutrinos. People talk about neutrino mode or antineutrino mode, but of course you cannot avoid contaminations on one hand, and on the other hand, the fluxes that you make are broad in energy, so they are not monochromatic, which means that on an event by event basis, for a single event that you detect, you don't know the neutrino energy that triggered that event. And the energy is very important. It's down here in the oscillation probability. So in one way or another, experiments need to determine this energy in an oscillation analysis. For example, high energy experiments like NOVA or Dune in the future, the strategy they use is that they rely on what is called calorimetric neutrino energy reconstruction. So they see the lepton in a charge current interactions, particularly if this is a muon. Most neutrino detectors are well prepared to detect muons, and then they try to measure the hadronic energy that is deposited in the detector. And if you have a situation like the following, you have a neutrino interacting with your target, say a nucleus, which detectors nowadays have carbon, oxygen, argon. The new generation of experiments have argon. So you can have the following situation: the neutrino interacts with your nucleus, and then you have a proton emitted, and the proton have enough energy to be detected, and the rest of the system is a spectator. To begin with, this is not very common if you have neutrinos. If the collision is quasi-elastic, we will see it takes place essentially with neutrons. But okay, this can happen, and fine. In this case, if all the energy is taken by a single nucleon, reconstruction would work. I mean, I'm sorry, I said it wrong. This is exactly the case in which you start with a neutron, you convert it to a proton. This proton is emitted, and the reconstruction works reasonably well because all the hadronic energy will be concentrated and well measured by detecting and measuring the energy of this proton. But it's not so unusual that together with a proton, a neutron is emitted. Neutrons are harder to detect, they might be missed. And as a result, the energy that is measured calorimetrically, the energy that is reconstructed in the detector, is smaller than the true neutrino energy. This leads to a bias that can introduce systematic errors in neutrino experiments. So for these reasons, experiments rely, so they perform the steps starting from measured quantities, right? What you really see in the detector, you see light, you see electromagnetic currents. Going from there to the reconstructed neutrino energy, and from there to the inferring the neutrino energy. So to do these migrations, the experiments rely on their Monte Carlo event generators, which actually incorporate in one way or another neutrino interaction theory. So it is important for the experiment to have the best neutrino interaction theory in the Monte Carlo, because even if near detectors take data and they can help tune in the event generators, if there is some mismodeling in the generator, it can lead to systematic errors and to a failure to understand the data correctly. Okay, at this point, let me mention something. You might wonder. We heard yesterday from Professor Kajita. We heard the story about the discovery of neutrino oscillations. nothing was mentioned about neutrino interactions. Although, if you read the paper, you would see there the references to the work that was used in the generators. But still, there is a reason. The reason is that in this discovery path, the experiments were dominated by statistical uncertainties. So systematic uncertainties to which the interaction process contributes mainly were there, but they were not the limiting factor. Now this field is evolving towards what is called the precision era. So trying to measure oscillation parameters very precisely, look for the determination of the mass ordering, and in particular, I think CP violation. CP violation is probably going to be very sensitive to systematic effects. Actually, I remember when I started attending neutrino meetings, it was still when the last angle to be determined, theta 1,3 was still not known, and there were, again, as it was mentioned yesterday, people fear that this angle was going to be so small that you really would hit the system. You would start having issues with systematics. Nature was kind, and theta 1,3 was not as small as originally expected, but well, it might not be the case in the future. Now, so in case you didn't notice, this was the introduction motivation of this presentation. What I have here, well, this is not really the outline of these 2 hours. It's more of the list of topics that are covered in these slides. So I dynamically modified the slides, remove something, add others. Overall, they tend to increase, and I have too many, and I don't really expect to cover all these topics in the 2 hours. What I would really like to do is go slowly, paying attention to the detail. I would encourage you to ask questions that you might think are naive. They might be not, or that might be. As a matter of fact, most of you in your everyday work, you don't encounter this topic of neutrino interaction so often. However, path in science can be unpredictable. You might end up getting involved in a project where some basic knowledge of what we know well in this topic and what we don't know so well might prove useful for you. Okay, so let me then start with really the basis, the standard, the structure of the standard model, right? The electroweak sector. So we know that the standard model is an SU2 cross U1 gauge, has an SU2 cross U1 gauge symmetry, that when it is broken, then part of the vector bosons get mass, namely all the C and the W get massive, and the photon remains massless, and you have some mixing between the photon and the C boson. So this, what you see here, you have different terms. One term for electromagnetic interaction, one term for neutral current, another one with its complex conjugate for charge current interactions. Each of them comes with their combination of couplings. And in every case, you have the boson field, right, which is a vector field, coupled to to a current. In the case of, so to begin with, we have in the electronic sector, the electromagnetic current has the standard vector structure. So we have charged leptons and a gamma mu, because this is a vector, and then the second spinor. And this is the same structure for all the flavors. Now, charge current interactions, we only meet with neutrinos, and they have the typical V minus A structure. the same structure you have in the neutral current for neutrinos, pure V minus A. However, for charged leptons, we have different couplings in the vector and the axial vector part. In particular, the vector part has this combination, while the axial is -1. And it is interesting to notice that the vector coupling is much smaller than the axial one. This, well, we are always intrigued by this when there are big differences in values. As far as I know, this is considered to be accidental. It's a consequence of the initial unification of electroweak forces, and you end up with this vector coupling. And as far as I know, there is no deep meaning in this. Still, something to keep in mind. This cancellation will come up again later. Now, with this alone, we can already study the interactions of neutrinos with electrons. If neutrinos are muon or tau neutrinos, they can interact with electrons only via the exchange of C boson, that is with neutral current interactions. Instead, if you have the electron flavor, then the interactions can occur also by charge current interactions. This is probably many of you know that this is critical to have matter effect and the MSW effect. In addition, if you have antineutrinos with enough energy, they can interact with electrons, and in such a way that the W boson gets on shell. And in this limit, the antineutrino electron cross sections gets really high, much higher than any other interactions that neutrinos can have. And as a matter of fact, few years ago, the IceCube experiment published a paper where they reported the detection of just a single event, just a shower that was consistent with this scenario, with the production of an on-shell W. It was published in Nature, and to be sincere, I really wonder what's the big deal about this, in the sense that I think no one would have expected otherwise. I mean, whoever that has studied quantum field theory 100 knows that they will expect that if you have interactions in the T channel, you will also have the possibility, if you have enough energy, to put the W on shell. I guess that this was just a proof that they can detect that. In my opinion, that what would be really interesting, if they are lucky to accumulate enough statistics to be able to study this kinematics well enough. In that case, probably there is something interesting to learn. So you wanted to mention. Of course, of course. But in that case, it is not so relevant if you are exactly at the point where you put the W on shell, or higher, or a little, or little higher, or little lower in energy. You really want to understand what is this flux, no matter whether it is at the glass show resonance or not exactly there, right? Exactly. So from the point of view of astrophysics, my impression, it is not so relevant that you see this peak here. you want to really probe the whole region. Anyway, so now let's move to quarks, to the quark sector, right? So in the quark sector, okay, we have pretty much the same situation. We have electromagnetic interactions that are diagonal in flavor, and they are proportional to the quark charge. 2/3 if we have U, Cs, or top quarks, and -1/3 otherwise for the rest. In the case of neutral currents, now we have the interactions coming in these combinations in which we have the third component of this, the weak isospin, or the charge, now multiplied to twice the sign of the squared. And charge current interactions, they are different. They are different because they mix flavors. So, and this mixing is determined by the Cabibbo, which just I'm not going to discuss it in detail, but just to show one of the standard parametrizations of this matrix. So we have all possible mixing angles between quarks, and there is also a phase that accounts for CP violation in the quark sector. So there are many studies of again trying to measure the parameters of this matrix precisely, also CP violation, and we know that this is one of the mysteries, that this matrix is very different from its neutrino counterpart. What I would like to stress here, well, in particular, if you limit yourself to the lighter quarks, U1C and D and S, here in this matrix, you reduce this CKM matrix to a 2x2 matrix, which is parameterized in terms of a single parameter, which is the Cabibbo angle. So you get just a rotation in terms of an angle which is relatively small, which means that if we have a weak interaction with a W minus on a proton, for example, one can turn U quarks into D quarks. And this interaction is going to be proportional to VUD, or the cosine of the Cabibbo angle square. And it's relatively, it's enhanced because this angle is small. But one can also produce, and this is very specific of weak interactions. Only with weak interactions you can convert U quark into S quarks, and they go from protons to hyperons, to a lambda hyperon, for example, or from a proton to a proton K minus system, producing strangeness. So these processes are there even if they are slightly suppressed by the, well, slightly suppressed. They are suppressed by the value of the Cabibbo angle. Next, so now let's move to strong interactions. Strong interactions, the fundamental theory for strong interactions is QCD. It has a color SU3 symmetry, and we all know that QCD at large scales, at large energies, has a small, so the coupling decreases at high energies, and the theory is perturbative. But when we go to lower energies, it becomes non-perturbative, and eventually you get confinement. So you don't get to see free quarks, but they are confined into into hadrons. Okay, now what I'll do next is discuss a number of approximate symmetries of QCD that are very important to as an input for neutrino interactions. Although at this point it might not be so obvious, but trust me, they are important. To begin with, if you look at the QCD Lagrangian and remove, so I'm going to be focusing on the light quark sector. So I'm going to be considering U and D quarks mostly, which is what you get in normal matter. Eventually also everything that I will say is to some extent valid to the SU3 case, in SU3, flavor SU3 case, in which you include U, D, and S quarks, okay? So let's take the limit in which the quark masses are zero, which, as you can see here you have the values of the quark masses at a relatively low scale, 1 GeV, and you can see that indeed the U and D masses are very small. Compared to what? Well, compared to the raw meson mass or to the nucleon mass. Keep in mind 1 GeV. 1 GeV is the scale with whom we should compare. So you can see that clearly U and D quarks are really light. The strange quark is not so light, but still much smaller than this scale. So in this limit of massless QCD, the theory has is what is called chiral symmetry. It is symmetric under left hand and right hand rotations independently. And as a result, you get 16, 8 plus 8 conserved currents, which can be written as right and left currents, or they can be regrouped to get vector and axial vector currents. So here, and these currents are going to be all conserved in this limit, as it is indicated by the fact that the derivatives are 0. So just notice the way these currents are written. So I have a q bar vector. I'm now building vectors in the SU3 flavor group, right? So I have the vectors of flavor vectors written like this, and these currents are written in terms of the generators of the SU3 the generators of the SU3 fundamental representation, which are 8. They are the well-known lambda matrices. And as you let me remind you that the SU2 group is a subgroup of SU3. So you have on the top here lambda 1 to lambda 3. You can see what you get here are the Pauli matrices. So there is a subgroup which is an SU2 isospin group where all the symmetries, all the flavor symmetries I'm going to be discussing are even better than in the SU3 one, because the U and D quarks are lighter and their masses are closer to each other compared to the strange one. Okay, now what happens if we add the quark mass terms? So you break this symmetry, which I probably didn't mention, is called chiral symmetry. So the limit of massless QCD is called the chiral limit. I'll be mentioning it a lot. So then what happens when you add the mass is that the currents that I defined before, the vector and the axial currents, they are no longer conserved. You get these identities here, these two identities. So the vector current is proportional, it's going to be proportional to this, it's going to be equal to this combination in which you have the commutator of the mass matrix, which is just a diagonal matrix with the quark masses in the diagonal. And in the case of the vector current, you get the commutator of this matrix with the different lambdas, the different Gelman matrices, and in the case of the axial current, you get the anti-commutator. So these two equations are, I think they are nice. They contain a lot of information. So let me magnify them a little bit so that you can see them better. There are many consequences of this identity. First of all, in the chiral limit, let's start with the vector current. In the chiral limit, the current is conserved. I already said it. However, not only in this limit, because we have here a commutator in the limit where all the three masses are the same, so you can factorize out the value of this average mass, and this commutator is going to give you a 0. So we recover the symmetry in the case where all masses are the same. This is the SU3 flavor limit, which is the scenario in which the quark model was developed, and the classification of hadrons in terms of for example the lightest octet or the lightest decuplet can be defined. You can of course have, as I said, a better symmetry in which only the U and the quarks are equal. In this case, one has an SU2 flavor isospin symmetry, which is a very good symmetry of strong interactions. Now, at this point, okay, so no, sorry. Now, the axial current, unlike the vector current, the axial current is only conserved in the chiral limit. So there is no combination of masses that would make this anti-commutator be zero, except that the matrix is zero itself. So, and this actually, particularly in the old literature, you get to this scenario referred as the CVC, the conserved vector current, and the PCAC, partially conserved axial current, which simply means that the axial current is conserved in the chiral limits. That's the way one would understand this with nowadays with QCD. And the conservation of vector current is ultimately a consequence of flavor symmetries. They are valid in the limit of SU3 or isospin symmetry. Okay, this structure in terms of SU3 is useful. It's going to prove useful later on. So let me spend a couple of minutes rewriting the quark currents, the electroweak quark currents in terms of this basis. And if we do this exercise, we can see that the electromagnetic current can be written in terms of two of these vector currents, the one that goes with lambda 8 and the one that goes with lambda 3. They are both diagonal, right? So if I can go back to, yeah. So lambda 8 is here. Lambda 3 is just the tau 3, the Pauli matrix. So of course, only diagonal, only the diagonal part can be relevant for electromagnetic interactions because there are no changes in flavor. So you get this combination. This current is usually called the hypercharged current, and then there is this B3. Now, if we look at charge current interactions, and we take, for example, only the transition from U to D quarks, the one that comes with VUD, then this combination can be written now in terms of lambda 1 plus I lambda 2. So it is a combination of B1 and B2. So you can see that we get, so part, we get a triplet in isospin. Actually, these three components of the current, they make a vector in isospin space. They are the three components of a conserved current, which is something that will later on prove useful to relate form factors to known, for neutrino interactions to known form factors. So this is why this is relevant. You can do something similar with the neutral current. So the neutral current can be written with some coefficients in terms of B3, of the hypercharged current, and there will be an additional contribution from strange quarks, which in general is going to be small. Something very similar happens with the axial current. Again, we have that the charge current is given in terms of A1 and A2, and the neutral current is given in terms of A3 plus a strangeness constant. In this case, we don't have anything like the hypercharge contribution, or also, if you go to the SU2 limit, is also called the isoscalar contribution. This is only present in electromagnetic interactions. Good. So now I mentioned about chiral symmetry. Now let me discuss the following. So I mentioned that in the limit of massless QCD, we have chiral symmetry, which is broken by the quark masses. But there is another way, far more remarkable way, in which chiral symmetry is broken. And this is, one realizes that this is the case by looking at the ground state, at the spectrum of hadrons. And you can see that this ground state doesn't have the chiral symmetry of the Lagrangian. In particular, this chiral symmetry would mean that there are parity doublets. For example, what would expect that the row mass and the mass of the which has a spin and parity 1 minus would be close to the mass of the A1 meson, which has spin and parity 1 plus. These two masses are far apart from each other, so the difference between these masses cannot be explained with just the symmetry breaking the explicit symmetry breaking introduced by the quarks. It's not enough. Those masses are not so large. You also can see that there are light pseudoscalar mesons, pions and kaons mostly. Of course, the kaon is much heavier than the pion, but this we can understand because the S quark is heavier than the U1 and D ones. But both pions and kaons are much heavier than the scalar the light scalar mesons. For example, the F0, which is a very broad state, its mass is not very well defined, but you see it is between 400 and 800 MeV, much higher than the pion mass. And the same is true for this M kappa. This is supposed to be a kappa, which is again the corresponding scalar meson with strangeness, which is again almost twice, it's like twice the mass of the kaon. So the spectrum, so what we see in the experiment about hadrons indicates that chiral symmetry is spontaneously broken. So the SU3 left cross SU3 right is broken down to SU3 vector. And this symmetry breaking implies that there are Goldstone bosons, and the Goldstone bosons of spontaneous chiral symmetry breaking are pions, kaons, and the eta meson. This is a remarkable result of QCD. It is remarkable because it also allows to write an effective Lagrangian for strong interactions and eventually do perturbation theory with strong interacting systems in some scenarios. So what follows now, how much time I have left, do you know? Okay. So enough to describe chiral perturbation theory, at least in a nutshell. Yes, please. Through explicit symmetry breaking. So through explicit, exactly. This is actually, I was complaining to you might remember I complained to Gabriela when the other day she said kaons are not, they don't get their masses from QCD. Then what happens, I don't have the explicit expression now, it will show up later, but you essentially, so in the chiral limit, all these bosons that appear in this matrix here, I'm coming to it, they are massless. It's only when you introduce the quark term that they get a mass, and what happens is that their masses, for example, the pion mass is something like 2 f pi times pi. You have a combinations of the quark masses and this object here, which is I think it is square, which is the chiral condensate, right? So this object, it's what drives the symmetry breaking, and only when you have explicit, in spite of the fact that you have a finite value for the chiral condensate, if the masses are 0, your Goldstone boson masses are going to be 0. Okay, so back here. So chiral perturbation theory is the effective theory of QCD at low energies. So it is not renormalizable as the standard model. It is only renormalizable order by order. So your Lagrangians have an infinite number of terms, and each term comes with a number of parameters, which are called low energy constants to be determined from experiment. But in this way, you write the QCD Lagrangian in terms of hadronic degrees of freedoms, and specifically in terms of the Goldstone bosons. Of course, this has to the construction of this effective Lagrangian has to fulfill the symmetry breaking pattern, right? And this essentially means that your Goldstone boson fields are going to live in the Coset space. And a convenient parameterization for this field is the following. So you have an exponential of this 3x3 matrix that contains the Goldstone boson fields. And the simplest Lagrangian that you can write for this effective theory now is the following. You remember that if you have Goldstone bosons, this means that you need derivatives. You need derivative couplings in the Lagrangian, because the Goldstone theorem requires that in the limit in which when you go to zero momentum, amplitudes are going to have to vanish in the chiral limit. And to have that, so you need derivatives. So the simplest Lagrangian one can write for Goldstone bosons is the product of the derivative of this du field times its complex conjugate, multiplied by a constant that, as we will see later, is nothing but the pion decay constant. So this is the leading order Lagrangian. It is said that, so we can establish, I'm coming to that, a power counting, a hierarchy of amplitudes, which mean that amplitudes with a smaller number, with a smaller power counting are going to have an impact on your observables that is smaller, provided that the scale, the momenta involved in the interaction are small enough. So that is simply perturbation. You can do perturbation theory because you have a hierarchy of contributions, a hierarchy of Feynman diagrams. And in the case, in the simplest case of mesons, so the leading order Lagrangian has order 2 because it has 2 derivatives. You can write a more complicated Lagrangian involving 4 derivatives and a number of free parameters. This can be also extended to the baryon sector. One can include the lightest baryons, the baryon octet, proton and neutrons, but also hyperons in the formalism. It has minor. It has a complication, which is that you introduce the baryon mass, which is a quantity that doesn't vanish in the chiral limit. So you remember there was a gap, and only the Goldstone bosons become massless in the chiral limits. Other hadrons don't. In particular, the baryon octet doesn't vanish in this limit, and this creates a technical complication when you do calculations, when you do perturbation theory, because you get a scale that breaks the ordering of contributions. But this is handled by an additional finite renormalization of the amplitude. So essentially, this symmetry breaking is absorbed by your low energy constants. All other heavier hadrons are integrated out. This is the spirit of effective field theories. They are integrated out of the theory, and they will be encoded. Their information would be encoded in the low energy constants. Now, I was already mentioning power counting. You saw it in the Lagrangians. By the way, let me also mention that the leading order baryon Lagrangian with baryons is order 1 because it comes with 1 derivative, essentially. But then you can again construct Lagrangians with a larger number of derivatives. In general, the nice, so this construction is actually a theory, an effective theory, because you can systematically improve any the calculation of any observable that you calculate with this formulas. And this is thanks to the fact that there is a power counting. So you have an amplitude that is a function of your external momenta. If those external momenta are rescaled by a small parameter, so the amplitude is going to be scaled, but these small parameters to a power of n, which is called the chiral order. I'm not going to derive this, but just let me mention that this chiral order is given by the following expression. So the order is 4 times the number of loops that you have in your amplitudes, and that is easy to understand because in loops you have 4 momentum integrations. So you have in integrations of 4 momenta, so you get 4 times the number of loops. Then propagators are in the denominators. They bring they bring momenta in the denominator. If they are meson propagators, they are momenta squared. So we have minus twice the number of meson propagators. If they are baryons, it's just 1 momentum in the denominator, so minus the number of baryons in the denominators, plus the order of every vertex that you get in your amplitude, which is given by the order of the corresponding Lagrangian, which is again determined by the number of derivatives, essentially. Okay, just a simple example. All this machinery was developed by essentially, well, the leading people to develop chiral perturbation theory for mesons were Gasser and Leutwiler in Bern, and they studied that. So this led to a very detailed study of meson interactions. This is how this theory was born. Just to give you an example of this, how this power counting works, imagine you're studying pion-pion interaction, okay? So then you would have contact interaction coming from the leading order Lagrangian, right? This one here. So you can have like pi plus, pi minus, going to pi plus, pi minus. And this amplitude, the amplitude that you get here is of order 2, if you use the leading order Lagrangian to calculate it, because it has no loops, no propagators, just a vertex of order 2. But then you can improve your theory and go to order 4. And you can have a contribution like this. Now, we would be having here vertices of order 2, another one of order 2, one loop, so 4, 2 meson propagators, which means minus 4, no baryon propagators, and the 2 vertices, 2 plus 2, which makes an order 4. So if the momenta, the external momentum in these amplitudes are small enough, this contribution is going to be much smaller than the leading one. This is the philosophy. And again, it has a loop, so it will have infinities. These infinities are going to be absorbed in 3-level amplitudes of order 4. Well, what all this has to do with neutrinos? Well, I didn't mention, but let me say that in this theory you can couple your amplitudes to external fields. In this case, you extend the derivatives in the standard Welian field theory. Here I already wrote extended derivatives, and you can couple your theory to external fields, and in particular you can couple them to electroweak fields, and eventually do calculations for quantities that provide your input for neutrino interactions with matter. Okay? This I already did. So at this point, we have, how much time we have? Maybe this is the last thing I did. Yeah. So I think it was Gabriela who said yesterday maybe everyone should look at the pion decay in some detail at least once. So maybe I don't know if you have done that, but I have them in the slides. So maybe we can just look at pion decay. So let's consider pi minus decaying weakly into a mu minus and the corresponding anti-neutrino. So pions in terms of quarks are QQ bar combinations, and then these pions are essentially annihilated or fluctuate into into the weak boson, the W boson that then leads to the two leptons in the final state. So if we write a Feynman diagram for this amplitude, right? We have the electroweak Lagrangian, and we have a very well-defined weak vertex, right? So we have this Lagrangian that connects, let's say, the vacuum of the electroweak theory with a mu on an anti-neutrino in the final state. Then we will have a propagator for the W boson, which after fixing the gauge, it can be written in this way. And since we are here at low energy, so the energies involved are very small, we can write it in the static limit. So we neglect this term, we neglect the momentum dependence in the propagator, and just write the propagator in this way, which then is going to get together with the weak couplings that you have in the Lagrangian, will lead to the Fermi constant. Okay. So now we have the next vertex, the vertex that connects the pion with the vacuum. And here, of course, if we would think in terms of quarks, we would write something like this: terms that annihilates both the quarks. However, this would not give any realistic result because we are in the non-perturbative regime. And we know that essentially because the pion is a Goldstone boson, we know this matrix element has to be non-zero because the axial current connects pions with the vacuum because of the spontaneous chiral symmetry breaking. And the structure of these matrix elements, we don't need much to write it. So this particle is a pseudo-scalar. So the only quantity we have to construct this 4 vector is its momentum. There is nothing else. Actually, if we didn't reason in this way, we could go all the way, take the leading order Lagrangian coupled to axial currents, and we would get something like this for the axial current. So we would get that the axial current is the derivative of the pion field times a constant. And this square root of 2 comes from isospin. There is no big deal. So we essentially get f pi, and the derivative of the pion field gives you I times the momentum. So at this point, if we want to calculate the decay width, we need the amplitude squared. Okay, so we have to do the usual thing: take the sum over sum and average over all well, in this case is sum because they are in the final state. Sum over all the polarizations of the fermions, and we get the lepton tensor. Okay, and the lepton tensor has this structure. It has a symmetric part and an anti-symmetric part, which comes from the interference between the vector and the axial vector part. And then the hadronic tensor that is going to be contracted with the leptonic one, in this case, is very simple. It's just this matrix element here squared. So we get a factor of 2, f pi squared, and a product of the two the pion momenta. Now, think a rule of thumb that is good to keep in mind always is that if you have a lepton tensor, right, and you contract it with the momentum that is connected to these leptons for momentum conservation, so in this case, this Q that is simply P plus K, where P and K are the momenta of the outgoing leptons. If you contract this tensor with this vector, you're gonna always get masses squared. Okay, and this actually can be seen easily. So to begin with, here we have in this term we have already P. So we have the antisymmetric, fully antisymmetric tensor, and we already have P and K. So the momenta of the outgoing leptons. So if we contract them with Q, which has P or K, we are just going to have the momentum repeated. So this contribution is going to be 0. So we only need to consider the symmetric part of the electronic tensor. So we have, for example, we have P mu K nu plus the combination exchanging the indices minus G mu nu and the scalar product, right? K plus P. And this is going to be contracted with K plus P mu. So this is a simple exercise. Let's do it. Now P is, I'm calling P the mu. I'm going to be neglecting the neutrino mass, okay? So the first one is going to give me, so I'm contracting with P, so it's going to give, so I'm going to get here P dot K, right? This is the first. And the second with P, I'm gonna get P squared. P squared is M mu squared. Sorry, something is missing here. P dot Q times K nu, okay? And then M mu squared times P dot Q times P mu. Nah, no, I'm doing P dot Q times K nu, that's correct. Then then is P squared times again K nu. And the other term is going to be the other way around, okay? So it's P dot K. No. It's going to be P nu, okay, P nu, and then K squared, which gives you a 0, and K dot P. Is this correct? So no, it is, yeah, it is correct, I think. And from here we get K plus P nu, all this doses is lower in the index, times K dot P. So you can see that now we have a cancellation between this term, and this term, and we are only left with a term proportional to the mu mass squared, which then, if I contract it with the second Q in the hadronic tensor, I end up with K dot P, which is what is written up here, and the factors. I get F pi squared, Fermi constant squared, some numerical factors, and this combination, which then this product can be written again in terms of masses. So again, as Gabriela said yesterday or the day before, the fact that we get here the lepton masses is an indication that when this decay happens, so you end up with the wrong combination, the wrong helicity for the lepton, and the only way to flip it is through mass terms. So this is the reason why we ultimately get this mass here. If the leptons were massless, this matrix element would be 0. Then to calculate the decay in the rest frame, so we have the standard expression from the width in terms of phase space, and the result after doing the kinematics, I think Gabriela told me she did the phase space for you. So you end up with this combination here, which again is a trade balance. You have this lepton mass square here, and then 1 minus this difference. So this term, if the mass is smaller, gets larger, but at the same time, this term will be getting smaller. And this combination results in the fact that the decay in the muon channel, the probability, so the decay width is much larger than for the electron one. So if one would have here the electron mass, and again here, so this term will be higher, but this will be killed by the electron mass squared here. So in the end, if the muon, by measuring the pion lifetime, it is possible to determine F pi, the pion decay constant, which is around 92 MeV. And this is in QCD at low energies. This is a very fundamental property that appears essentially in every term of the effective Lagrangian. Okay, I think this might be what time is it? So this be a good place to stop. So then when we reconvene, I'm going to start with some general properties of neutrino cross sections. Okay, thank you.
Lecture.
Is that F file has something to do with form factor?
No. Okay. Well, F pi is essentially also you can calculate different contributions to F pi. In the sense you can calculate corrections, loop corrections to F pi, and okay. Let me put it in this way. Strictly speaking, the F pi that appears in the Lagrangian is the value of F pi in the chiral limit, not the experimental one. Okay, that's a good point. Thanks for the question. So if I had been more rigorous in the Lagrangian, I would have written F0 or F pi 0 or something to indicate that's F pi in the chiral limit. At leading order, its value is the one you get from pion decay. But you can, this theory allows you systematically improve the determination of F pi, including corrections that come essentially from the quark masses, from explicit symmetry breaking. Thanks.